So I'd like to introduce Nathan Dunn, GE Grid Solutions, Global Product Manager, Microgrids and Distribution Solutions. Just to say a little bit about Nathan, in 2019, he rejoined GE's grid automation business as a business development service leader. And currently, he's the Global Product Manager for Microgrids and Distribution Solutions. Previously, Nathan spent 3 years with the Schweizer Engineering Laboratories as a regional sales manager, preceding his time with the SEL. Nathan worked for 10 years he worked for 10 years at General Electric inside multiple businesses, performing various roles, including service manager, global operations leader, and field engineer. Nathan has earned master's degrees in administration, an MBA in University of Maryland, and a bachelor's of science in electrical engineering technology from the University of Pittsburgh. So Nathan, I hand over to you, please.
Okay, well, thank you. Thanks for the introduction and the opportunity of allowing me to speak today. I'm going to share my screen here as well as I talk. So, all right. So for today's presentation, I'm going to be covering the effective and optimized microgrid controls and optimization. A few things. We're going to start with some of the trends and the definitions. What is a microgrid? How does that differ from renewable integration? The benefits, challenges, and drivers that we're seeing in this market with regards to getting these systems online. We'll go through the project lifecycle, and then as well as some of the operations and optimization considerations that companies and utilities need to take into account when trying to integrate these onto the grid. And then also we'll look at a few use cases that we've done, and then leave some time for some Q&A, hopefully at the end. We'll start with some of the trends. I think everyone on this, in this room probably understands what's going on today, but we're undergoing a transition really due to electrification and the growing energy demand, really driven by rising populations and standard of living, as well as the electrification in vehicles in some regions. From a decarbonization standpoint, this has been driven by customer demands, country, state, and global policies, as well as some renewable energy targets, and also corporations that are looking to implement carbon neutral programs or sustainability initiatives. We have digitization also happening at the same time, driven by the increase in the number of sensors and information that we can gather from the grid, and the ability to perform analytics and leverage that information to make informed decisions. And then decentralization through the rise of renewables and integrating those onto the grids. These trends are really challenging the existing power system model, which has been geared more around central large-scale generation and is accelerating the need for effective renewable integration and microgrid solutions. This slide just kind of illustrates the differences on how traditional energy solutions and non-wire alternatives address the growing energy demand and the rise of really that capacity during peak times. With the traditional model, the centralized generation, the increase would drive a need for CapEx spending in order to get the energy to the customers. But with the non-wire solutions or decentralized energy through renewables, whether that's storage, a microgrid, or even demand response or energy efficiency programs, which some companies have put in place, this rising demand can be offset by the local generation or demand reduction, really preventing the need to upgrade some of the transmission and distribution systems. And this would provide additional reliability to those customers inside or local to those energy sources. Here are two charts. I'm sure this was talked about earlier, but they're from Navigant Consulting that really illustrate the growing DER and microgrid markets in the Middle East and Africa. That's how they had it broken out. This is really a shift away from the traditional centralized power. And as I mentioned before, it will change the architecture of the grid from a centralized to a distributed two-way power flows. It also really enables customers not just to be ratepayers, but possibly participators in the market. And also, this is kind of driven by the customer's motivation, which may no longer just be cost, but cost plus renewable generation, emissions reductions, reliability, efficiency, in order to ensure that reliability is maintained during this transition. We need to make sure that we have effective and optimized controls that are required to really integrate these systems into the grid. So we talked a little bit about the trends, the growing demand of microgrids and renewable integration. But what's really the differences between these two types of solutions and some of the things to consider? From renewable integration, it really focuses on producing power optimally and getting that power onto the grid. Where a microgrid may look to balance the energy supply and demand inside its boundaries with regard to the point of interconnection with the grid. We'll go into microgrids in more detail as we go forward in the next slide. However, from a functionality standpoint, both systems look fairly similar in terms of the controls and optimization functions that customers want, as well as the need to really integrate these systems, whether that's into the energy markets or to a utilities DMS system. A renewable integration solution, for example, they may want dispatching capabilities of that wind farm or even a hybrid power plant, where a microgrid really looks to manage its energy inside those boundaries, but also has the capability of being dispatched onto the grid when required or called upon. Since the functionalities are kind of similar and microgrids do incorporate the loads as well, I'll spend most of my time talking about microgrids, but at the end, some of the use cases do reference some of the renewable integration opportunities or solutions that are out there. So just high level, what is a microgrid? It's really defined as a group of interconnected DER resources, mostly made up of renewable sources and loads that are centrally controlled and can connect or disconnect from the grid through one point of interconnection. So we'll go into the benefits and some of the challenges. So first off, why a microgrid? As I mentioned earlier, this growing energy demand really puts stress on our current network and the infrastructure, and the increasing trend of this renewable integration, as well as some of the external factors out there, whether that's weather or customers' need for reliable power due to the cost of downtime and the effects on the system when that happens, has really driven the need for these types of solutions. Some of the main drivers that are out there are resiliency, sustainability, and economics, but those change per customer segment, which we'll see here on the next slide. I like to think of this market across 5 segments. In the US, you have military, which is a large driver of the North America microgrid market. But elsewhere, you have the C&Is and the industrials, whether that's hospitals, residentials, and commercial facilities. You have islands, whether that's a remote island or even an islanded community inside of a country that's not connected to the grid. You have campuses, whether that's large corporate campuses or college campuses that have some existing assets already in place that they can leverage to build a microgrid. And then you have utilities. Each of these segments are really looking for the different outcomes, which are listed here. I'm not going to go through them all. But all these outcomes can be achieved through proper design, controls, and optimization of their energy assets and loads inside the facility. So looking at the project lifecycle, a lot of these projects kind of go across the various stages, and that's where some of the difficulty lies. And a lot of it may be up in stage, 1 through 3. And so it really starts with a business case, the feasibility study, the analysis of the economic analysis, the simulation of the, let's say the load profile, what type of resources are needed, will the solution have a return on investment? Does it meet the cost of generation that the customer is looking for? And so once you get past that business case standpoint, you start getting into design. And what's the system going to look like from an engineering perspective? How much is it going to cost? What all pieces need pulled together? The size of the assets that different companies are looking to include in their package, and then it goes out to financing if that's needed. And most of the time it is. And so a lot of these projects include some type of financing, whether it's through a PPA or maybe on a microgrid. They're looking for more of an energy as a service or microgrid as a service style package, where the let's say the vendor not only owns the assets, but they operate and maintain the assets inside the customer's facilities. And then from there, we have the execution stage, which we have from an EPC perspective, doing this turnkey, pulling together all the pieces, integrating all the controllers together, commissioning, testing, validating, and then through that you have the services where you continually maintain these assets throughout their life cycle. From an operations standpoint, the outcomes that the customers want really drive the operating strategy and the functional requirements of a microgrid. Typically, a microgrid has two steady state operating modes, grid connected and islanded. But as I mentioned, some systems are always islanded. And so it really depends on the situation at hand. The microgrid controller should safely and reliably transition between these steady state operating modes in order to disconnect and reconnect to and from the grid. And depending on the requirements, this can be done seamlessly or can involve some type of short-term interruption. But again, that goes back to what the customer is looking for and how that is implemented. Some of the core functions of a microgrid control system that need to be performed in the steady state operating modes in order to effectively manage the network are dispatching and disconnecting and reconnecting from the grid. Dispatching during the steady state mode is where the control system is managing the frequency, the voltage, the power factor, the power flow on and off the grid when they're grid connected, and also optimally dispatching those energy assets. They could be dispatching to maximize time of life if the system does go into islanded mode. They could be optimizing to reduce energy cost or to reduce emissions or to maximize renewables. Depending on what the customer is looking for, you could optimize your system or set of assets to get that outcome out of it. And that also leads into the various capabilities and how the system is designed as well. And I see these controls happening across 3 levels. And so we look at the 3 levels of controls in most microgrid systems. At the top level, we have what I consider the tertiary controller. This is really your optimization engine. It's doing economic dispatch. It's participating in the markets. It's doing 15-minute ahead, hour ahead, day ahead schedules that it's sending out to the microgrid controller, which in many cases is our secondary controller. That secondary controller is interacting with all the relays, all the primary controllers to coordinate and control the system, whether that's through managing the voltage, managing the loads, synchronizing the system. It's really the brain of the operation. That's main concern is following, taking in a schedule from the tertiary controller, reading what's going on out in the system and the status of all the assets, and trying to comply with the tertiary controller, but its goal is to maintain reliability, right? And so it's looking at the live data. If something changes, it would report it back up to the tertiary controller. And then on the lower end, we have the primary devices. These are our relays, any type of primary asset controller, inverters that the microgrid controller would be communicating to gather information and to send commands to operate the system in a central manner. Here's just a few functions. I'm not gonna dive into all of them, but these are some functions that you could look for in your microgrids, whether it's and even inside renewable integration, right? Power factor management, synchronizing, islanding from the grid, managing reserve capacities, black starts, participating in the market, forecasting solar generation. And so these are all items and functions that should be considered when connecting these systems onto the grid or deploying them for customers. Here's just an example control system architecture that a typical system may have. You have the utility system really at the highest level. Maybe that's their DMS or ADMS. You could have even the ISO or the external markets communicating into the optimization engine, which is our tertiary controller, which we talked about, which talks down to our microgrid controller, which connects out to all those primary assets, which we mentioned. And how these controllers work together and the communication style that's chosen can really, drives the outcomes that our customer is looking for. So I'm going to go through a few use cases here and then hopefully leave some time for questions at the end. The first one is renewable integration. So we didn't touch on it a whole lot. From a renewable integration standpoint, sometimes it's just dispatching power, getting that power onto the grid. And so here's just an example where, let's say you have multiple different renewable assets, whether it's wind or solar. They each have their own controller. Maybe they're installed at the same time. Maybe they've been installed at separate times, and they're all connected into the same substation at some point. From a utility standpoint, how do they communicate to all those devices to leverage them together to get what they want? And so if they can dispatch them all centrally, maybe equitably, maybe they want to, not curtail 3 of the sources and only use 1 of them. Maybe they want to equitably utilize them based on their megawatt ratings. And so this is a way to centrally dispatch these units to get out of the system what you want. And so you could dispatch for voltage or reactive power to provide support onto the grid. Maybe it allows you to participate in reactive power markets that are out there. You could equitably dispatch, or you could dispatch on priority. You could also look to do volt-var control. Can you get some of that capability out of your assets before you have to control, say, a downstream tap changer? And so these are some items that should be considered when pulling in multiple renewables or trying to control them centrally out of your, let's say, your ADMS or DMS system. And through that, by leveraging these assets together, and also, with renewables being intermittent and being able to control them in a more centralized manner before operating some downstream tap changers, you're really increasing your life of the downstream assets. It has the ability to really increase your revenue by participating in maybe reactive power markets, and also gives you more flexibility and control of these assets. Here's just an example of a project that was done with a European utility on a 200 megawatt, 5 wind farms that totaled 200 megawatt. Same solution that we talked about, integrating this into the ADMS. The wind farms were owned by different companies, and so they wanted to make sure they were dispatching them equitably. They weren't curtailing 2 of them and only using 1 of them, or using the other 3. And so they wanted to make sure it was fair the way they were being dispatched. And so by implementing a solution similar to this, where they could dispatch them for voltage, power, reactive power, and power factor, and then it also really limited the number of operations on their tap changers on their line, as they were able to have a central controller that really worked with the local wind farm controllers to get the capabilities that they were looking for out of those assets. Another big benefit of something like this is really integration into the ADMS or the DMS, which helps the utility manage some of these assets. Here's just a short example of a remote islanded microgrid, and this is on the small side. And so, we talked about maybe some big renewable integration, but there's also a lot of small communities, whether they just have some small solar, a diesel generator, maybe even a small wind turbine. In this case, I think it was 100 kilowatt wind turbine, so nothing of the large scale, really looking to maximize renewables. And so use all the renewables they can. And if they have to offset by running a diesel generator, they will. And by doing that, they greatly reduce their cost of energy, increase their energy security because they didn't have to rely on fuel as much, utilize the battery to store their excess renewables when they were able to. And then by forecasting future solar, I guess you could say, the solar production, that helped them manage the state of charge of that battery on a daily basis. And then the last example I have here is more on the thermal hybrids. And so I know the focus is mainly on renewables, but the goal of increasing renewables, one of the things that customers are looking for is still the low cost, the reliability, and also availability. And when you pair renewables sometimes with a thermal source, you definitely, from an availability standpoint, an efficiency standpoint, and sometimes lower cost, it's a really good solution that we're seeing a lot of customers move to. And so this is an option similar to how a remote community might have used the diesel, which is more on the inefficient side. From a large scale standpoint, using some type of gas turbine, that again, the system's goal is to offset or to maximize renewables, but from a utility standpoint, how they want available power, when the wind's not blowing, the sun may not be shining, you would still have that thermal to keep the power from being as intermittent as it may be. Here's just yep, go ahead,
Nathan. I'm very sorry, but we will have to move forward. So I'll give you another minute to kind of wrap up.
This is my last slide, and so I won't. I'll just leave time, see if there's any questions. This just kind of shows the different values as you add these assets together.
Yeah, we'll have to take the questions online.
Okay.
As the next panel would have to come up now, but please take one more minute to wrap up so that we can.
Yeah, just high level from when we start thinking of our renewable assets, and whether it's thermal with a battery, or you add in storage or other wind and PV, the flexibility, the availability, and the functionality you can get as you pair these assets together continues to increase. And so that's just something to think about as you're looking for whether it's more reliable, less intermittent power onto the grid. So.
Thank you.
That's all. So thank you so much again for the time today.
And we thank you also so much for the knowledge shared. I'm sure a lot of people find this very valuable and useful. And I'm sure you'll be receiving a lot of questions also by email, which we will share with everyone as they come in. So thank you so much. Thank you.